All right, today we're going to crack two really cool physics puzzles all about electrical resistance. We're going to see how the exact same components can create wildly different outcomes, and then we'll play detective and see how a simple graph can uncover a hidden secret. Ready? Let's dive in.
So let's jump right into our first challenge. Picture this. You've got 4 electrical parts, and your mission is to wire them up to get the absolute highest resistance you can, and then, using those same 4 parts, rewire them to get the absolute lowest. How is that even possible?
Okay, here are our puzzle pieces. We've got 4 coils, and their resistances are 4, 8, 12, and a pretty beefy 24 ohms. Now, the secret here isn't in the coils themselves. It's all about how we cleverly arrange them. To figure this out, we really only have 2 main strategies: connecting in series or in parallel. A series circuit, well, that's like a single-lane road. The current has no choice but to go through every single component, one after the other. But a parallel circuit, that's totally different. It's like that road suddenly splits into 4 express lanes. The current gets to choose its path before it all merges back together.
So if we want the absolute highest resistance, which way do you think we should go? Yep, the series circuit. We're basically going to line up these resistors and make the electrical current fight its way through every single one. We're creating the biggest electrical traffic jam possible.
And you know what's great? The math for this path is just beautifully simple. When resistors are in a series, you just add them up. That's it. So we just take our 4 values, 4, 8, 12, and 24, and add them all together.
And boom, there it is, our first answer. By connecting these coils end to end, we get a maximum total resistance of 48 ohms. See? First half of the puzzle solved.
Okay, we found the highest resistance, but what about the lowest? This time, we want to make it as easy as possible for that current to flow, and a parallel circuit is absolutely perfect for this, because it gives the electricity a bunch of different paths to take all at the same time. Now, I know the math here looks a little more complicated, but the idea is just as solid. We're not adding the resistances, we're adding their inverses, so 1 over each value. Let's walk through it. We find a common denominator, which in this case is 24, add up the fractions, and we get 12 over 24. And then, and this is the most important step, we flip it upside down to find the real total resistance. And just look at that. By using the exact same 4 coils, but just arranging them differently, the total resistance plummets all the way down to just 2 ohms. I mean, that's a massive difference from our 48 ohm series circuit. Puzzle number 1 is officially cracked.
All right, on to puzzle number 2. And this one really does feel like a detective story. We've been given a bunch of clues. These are data points that connect voltage and current. Our job is to use a graph to figure out the hidden value of a resistor.
You know, every good investigation starts with setting up the scene, right? For us, that means just drawing our simple X and Y axis. This grid is going to be the stage where all our clues come to life. Next up, we have to label our axes, and this part is absolutely critical. We're putting voltage, that's V, on the horizontal x-axis, and we're putting current, or I, on the vertical y-axis. Getting this right is honestly the key to solving the whole case. Okay, scene is set. Time to look at the evidence. We've got these pairs of data, right? Like when the voltage is 1.6 volts, the current is 0.5 amps. Or when the voltage is 3.4 volts, we get 1.0 amp. Each one of these pairs becomes a single point on our graph. It's a piece of evidence. We're going to plot super carefully.
So once we plot all our clues, you'll see a clear pattern emerge. We can actually draw a straight line that connects them all. And the big secret to finding that resistor's value, it's hidden in the steepness of this line, what we call the slope. So what is slope, really? You probably remember hearing rise over run. In our detective story here, the rise is the change on our vertical axis, which is current, and the run is the change on our horizontal axis, which is voltage. So it's just delta I over delta V.
This seems pretty straightforward, doesn't it? I mean, the slope connects voltage and current, so it must be the resistance. It just feels like the obvious answer. But is it the right one?
Nope, it's not! And this, my friends, is the huge plot twist in our detective story. The slope is not the resistance. This is a classic trap, and it gets a lot of people. But once you see why, it's going to make perfect sense.
Okay, here's the big reveal. Look at this. The slope of our graph is current divided by voltage, I over V. But the most fundamental rule in electricity, Ohm's law, tells us that resistance is voltage divided by current,
V over I. Do you see it? Our slope is literally the upside-down version of resistance. So to actually solve this mystery and find the true resistance, we have to flip our slope. The resistance isn't the slope itself, it's 1 divided by the slope. It's the run over the rise, not the other way around. So when we actually apply this to the data from our line, we take the total change in voltage, which happens to be 6.8 volts, and we divide it by the total change in current, that's 2 amps. And the result? The hidden resistance value is 3.4 ohms. Case closed. So, we solved both puzzles. What are the big ideas we should walk away with? Let's just quickly recap the key rules we've uncovered. First up, series circuits give you a single path, and that gives you the highest possible resistance. Easy. Second, parallel circuits give the current options, and that means you get the lowest possible resistance. Third, Ohm's law is your best friend. R equals V over I. And finally, never forget the plot twist. On a graph of current versus voltage, resistance is the inverse of the slope. So you now hold the fundamental rules for actually controlling electrical flow. And this isn't just some abstract idea from a textbook. This is the blueprint for pretty much everything, from the tiny circuits in your phone to the wiring in your house. So the only real question left